All right, we're good. Can I have that bag?
Yeah.
Okay.
Worse, I'm screwed.
So here's
Sorry, I was being funny.
okay. So I was excited about it. So today we're finishing the last of kind of the theory on rates and how they play out, and then going to work out well because then Monday we'll start like a 3-day lab. 3 days.
That's so many days. Wait, does that mean there's not a lot of homework Monday and Tuesday?
That means on those, yes.
There's a lot.
Oh,
When is
That
that?
was a 3-day lab. So
Okay.
It's a 3-day.
Big person.
you're so kind.
I'm really like
I'm so benevolent.
For safety.
it's just
Something somewhere went horribly wrong.
so.
We will play like.
Okay,
What did you
so someone asked about question
53.
Good.
Where's 39? Okay.
So let's talk about 53, mainly because of the fact that this is what you're gonna have to do as part of the lab next week. So let's look at kind of the big picture.
Increases because,
So you've got,
well, I thought that meant the beginning of concentration. You know how it takes however long.
that's what I asked. Now,
I
here,
didn't think she was hero. I asked if she was so
okay, all I saw was this, okay? Oh, I'd like to take one
I
too.
don't know. I don't.
So here's the bigger picture on this problem.
Oh, we don't know. We don't.
Is that if you look at the trend and the temperature in Kelvin, you're going from 195 to 370, okay? So the temperature is going higher and higher and higher. Now, what you'll notice on the value of K is that the value of K is also getting bigger, okay? Now, here's the reason why. If you look at, let's say, just to make it simple, let's say it's a first order reaction. So R equals K times just the concentration of, say, NO. Let's just say that's it. So as the temperature increases, your rate's going to go up because of the fact that the molecules are moving around faster. They're going to have more kinetic energy. You're going to have more collisions. So if the rate gets bigger, and it is with a higher temperature, especially at this lab that you're going to see, you're going to do next week. It's very, very temperature dependent. So as that rate gets bigger and your concentration stays the same, the only way mathematically that works out is if that rate constant also increases. Okay, that's the only way it works. Okay, assuming that you're starting with the same concentration. So that's why that is lowercase k and not uppercase k, because uppercase k would only exist in equilibrium. This is why we use lowercase k. This guy's rate constant. So the value of lowercase k is dependent upon temperature because your rate is dependent upon temperature. Okay? So that's why if you look at that chart, you're going from 1.08 times e to the 9th up to 35.5 e to the 9th. So you're increasing this thing by like a factor of over 10, okay? So that's changing quite a bit. So here's what you got. What you're after is this activation energy. So you got the natural log of K is going to equal negative E sub A over R times 1 over temperature in Kelvin plus the natural log of A. For now, don't worry about that. That's just your y-intercept on the graph, okay? Don't worry about that part of it. What you're after is the activation energy. That's what you're trying to find. So what you're going to do is you're going to draw a graph where you're going to have the natural log of the values of K. This isn't, you're not doing this to figure out if it's 0 order, first order, second order, nothing like that. Mainly because of the fact that you're not graphing this as a function of time. We're not doing this to figure out the order of the operation. You don't even have time on the chart, okay? You couldn't graph it as a function of time if you tried. So here's what's going to be important. Down here, that's going to be 1 over the temperature in Kelvin, which means these values are going to be pretty small numbers, right? So in a situation like this, you could do like the little break where you say, okay, hey, I'm just going to focus on these values. So these, since you're taking 1 over the temperature in Kelvin, those are going to be pretty small numbers. So you're going to plot these points with a ruler. You're going to draw a line of best fit, okay? You are going to pick points that are on the line, okay? You are going to pick points that are on the line. Now, if your data points happen to be on the line, cool, okay? But that's the whole point of drawing a line of best fit. So you're going to find this slope. So when I did the slope, mine worked out to be around, what was it, like negative 1.5 times 10 to the third Kelvin, okay? Mine worked out to be around that point, okay? That's kind of what I had as my slope.
Oh, I love that.
Uh-oh, spaghetti.
Oh, I love that.
Okay.
That's beautiful.
Like that?
Oh, I love that. That's great. That's great.
I think he might love that.
That's exactly that.
Okay,
Thank God.
okay. Wow, I have never seen someone that excited about finding a slope.
Thank God.
Okay, slope be praised. Okay, so here, but that isn't the activation energy. Okay, even though it's Kelvin, that isn't even the temperature. Okay, look, do not look at this and go, oh, that's the temperature. No, your temperature, it has units of Kelvin, but it's not the temperature. It just makes the units work out. Okay? Let's go with it. Embrace the magic. Okay? Now, here's the whole point. This negative V sub A over R is what the slope is. Okay? Because this is a y-interceptor form of y equals mx plus b. Okay? So this is a mathematical operation. Oh, okay. The slope, which you just found, like in my situation, much to the happiness of Charles Shortcut, I got negative 1.5 times 10 to the third, about that, okay? So if that's your slope, which it is, then, now this is where you have to choose wisely in terms of R, okay? Because there's 2 main values of R. You need to use the one that's 8.314 joules per mole Kelvin, because you're looking for activation energy. You are looking for joules. So this is why the units have to work out like they do. So you've got that slope, which is in Kelvin, and then when you multiply it by joules per mole Kelvin, then the Kelvin cancels out. You're left with joules per mole. That's what activation energy is measured in. Okay? Like that? Like that? Now, so your activation energy, if you're in joules, should be a not so good GPA times 10 to the 4th. But there's some deviance on that depending upon which points you pick for your slope. Okay? If you're in kilojoules, it's around 12. Okay? I don't care which one you put it in, just let me know, hey, am I in joules or I'm in kilojoules? And once we get more into thermodynamics, that's going to be vitally important that you keep track if you're working in joules or kilojoules, because they mean completely different things. Okay, now let's talk about question 25 out of the book. So if you look on that one, let me open up the book, because this is a little bit wonky, but not bad. So if you look at what's happening on 25, so basically you're producing water. So you've got, that's what you're doing. You've got 2H2 plus O2 yielding 2H2O. Now, you all have seen this reaction take place. This takes place very, very rapidly, right? you light it on fire, bam! It isn't like, oh, it slowly turns and the explosion happens very slowly. No, it happens very, very rapidly. So, again, oddly enough, you have to start with the rice chart. Hey, what's my reaction going to be? So if you look at the information, it says hydrogen is burning at the rate of 0.48 moles per second. Okay, that's a pretty good clip, okay? So if you consider the fact that if you had 1 mole of this is about the volume, okay, this would be 1 mole. So you're consuming about half of this box of gas per second, right? That's a decent clip, okay? Half of this box per second. So what that means is in 2 seconds, that's how long it would take to burn a box full of this, right? Just to give you some perspective. So, what you're looking for on this is that what is the rate of formation of the water vapor, okay? So, here's what's happening. So you've got the oxygen and the hydrogen. They're bopping around. Bless you. You light the match, bam, the reaction starts. So what's happening is that they want to know 2 things. On the first thing on A, says what is the rate of formation of the water vapor? Then the partial pressure, no. That was the wrong one, 25. Oh, it is 25. Sorry. It says, what is the formation of the water vapor? So here is the story. So if you look at this in terms, and I kind of did the full thing when I worked this out. So the first number is 0.48 moles per second. So that's the rate at which the hydrogen is being consumed. Now, since these have the same coefficients, what do you think is going to happen to the rate of formation of water?
Would be the same.
That's going to be the same thing. It's just stoic. Okay, hey, the coefficients are the same. So the rate at which you consume hydrogen is the rate at which you would produce water. Okay? Now, what would you do to find the rate at which the oxygen is consumed? It'd be half. Ah. Oh, there you go. Now, when you get to B, okay, B is a different reaction. So you've got 2NO plus O2 yielding NaCl. So, when you look at the numbers that they've given you, first off, let's talk about torque. And we're going to get to gas laws here before too long. If there's ever a physical quantity in science that has an identity crisis, it's pressure. It could be in kilopascals, pascals, inches of mercury, millimeters of mercury, PSI. There's like 6 or 7 major ways that you can use to measure pressure. This happens to be in torque. Now, it's kind of handy if you can visualize how this reaction is taking place. So you've got 2 nitrogen monoxides that are floating around, and they're going to have to collide just right with the oxygen to produce 2 NOCOs. Okay? And this is what we're going to talk about today. This type of reaction is actually fairly rare, mainly because it's like a lock and key. And you've got like the 2 NOs, which have to align themselves just right to collide with the oxygen. And then you got to break the bonds that hold the oxygen together so that then you produce NOCl. So this reaction is fairly tough to do just because of the mechanism involved, and everything has to collide just right. You got to break the bonds. So it happens, but it's tough to do. So if you look at what you've got, so the partial pressure of the NO is decreasing at the rate of 56 torr. So this is decreasing at 56 torr per minute, okay, which is relatively slow because this reaction doesn't happen very quickly, mainly because of the fact that it's changing. It's just a tough reaction to pull off. So what it wants to know is then what is the rate of change in the total pressure of the vessel? So here's what you have to think through. So you know this number, okay? You've got this. So imagine what's happening inside this vessel. Remember, pressure is created by particles that are bouncing off the walls. So you've got your NO, which are bouncing off the walls. You've got your oxygen, which is bouncing off the walls. And then you've got your NOCL, which is bouncing off the walls, okay? So as these get consumed, you're decreasing the pressure that's created by the nitrogen monoxide and the oxygen. So that pressure is becoming less because they're getting consumed, okay? The pressure from the NOCl is increasing because you're making more of those. So you're dropping the pressures from the oxygen and the nitrogen monoxide. Those pressures are going down. Your NOCl pressure is going up, okay? Got the visual. Two things are dropping the pressure, one thing is increasing the pressure. So if you look at this in terms of, all right, there's my big idea. So if you can figure out the rates at which things are decreasing, and then compare that to the rate at which something is increasing, then you can make an overall comparison in the change in the pressure. Does that make sense? Okay? So if you look at this, you've got your NO, right? So if that's at 56 torr per minute, what's the rate of increase in the pressure of the NOCl? Yeah. So this is dropping at 56. That's increasing by 56. Now, if that was the only thing involved, if that was it, if that was the only thing involved, what would happen to the change in pressure in the vessel? It wouldn't change because, all you're doing is changing one type of gas for another. Okay? So if it was just that dropping and that forming, wouldn't be a big deal. But this is where you've got to do some stoic. So if this is dropping at 56 torr per minute, what's the rate at which the oxygen is being consumed?
28.
28. So you've got two things that are dropping, okay? You're dropping at 56 torr per minute and you're dropping at 28 torr per minute. But you're increasing at 56 torr per minute. So what's going to be the overall change?
Down 28 torr per minute.
There you go.
Do you want a negative?
Oh, yeah. Yep. Okay, does that help on that one? Okay. There's another one kind of like that, which is 34 on that photocopied page. It's a similar type idea. So on this one, you have this hypothetical A turning into B plus C, okay? So this is where, again, I beg of you, just don't get wrapped up in the numbers. Look at this in terms of a bigger picture. So on this one, it's zero order, which makes sense because of the fact that, hey, it's just A decomposing. It doesn't have to collide with anything, it's zero order. Now, because it's zero order, what would happen to the rate of the reaction if I doubled the concentration of A?
Nothing.
Absolutely nothing. The concentration of A does not matter. Okay? Now, zero order with respect to A, and you have the value of the rate constant, an expression, an experiment was run at 25 where A naught equals 1.0 times 10 to the minus third. Now, here's where you need this. This is 1.0 times 10 to the minus second moles per second. There's a rate function. Got that. Now, here's what you have to look at. Is that if you look at like a rice chart, okay? Got a rice chart. No, that's 5.0, not 1.0. Where did that come from? Hold on. I think I got excited about the ice chart. Now, here's the story. What you have to do first on this, because you know that it's zero order, okay? What you need to figure out is to do this on A. The first thing they want you to do is write the integrated rate law for this reaction. So what's your integrated rate law going to look like? R is going to equal what? Okay, and then if you really want to put A on there and put that to the 0, you can. That's technically the formal version of this. Okay, if you really want to get scientifically correct, that's what you need to do. Or you can just put that. Now, if I do this, is that the rate law or the integrated rate law? That's rate law. What do they want? They want the integrated rate law, right? So that has to be written in terms of the integrated rate law. This is why you have your handy dandy chart. I personally am not on the test. I'm going to tell you straight up, I'm not going to ask you anything involving 0 orders, okay? If I do, which I do not, I would give you that because 0 orders aren't on your sheet. So if you look on here on the kinetics, okay? So, oh, they did actually change that. So it's got second order, first order, and then 0 order. And what they give you down here is the half-life of first order reactions. They don't even give you the formula for the other ones. So you just have to know, oh, here's the formula for the half-life if it's first order, because that's what most reactions are. So, when you do this, and then once you get that done, then you need to figure out, let me remember what this is. On C, on B, you want to find the half-life. And the half-life on that should be something times 10 to the minus second, okay? At a not so good, horrible, bad GPA times 10 to the minus second. Then on C, they want to know, calculate the concentration to B after 5 times 10 to the negative third seconds has elapsed. Now, here's what you got to do. When you do this and you plug in that time, you're going to get the new concentration of A. Okay? So trust me on this one. If you do that value, if you plug in those numbers into the 0 order reaction, you get 7.5 times 10 to the negative fourth as your concentration. Okay? Now, here's where this gets a little bit wonky. Because of the fact that on this one, you know that the initial concentration of A is 1.0. It was the half-life that I screwed up. That is 1. Hold on. That's 1. So what you know then is at the end of that amount of time, that concentration of A is 7.5 times 10 to the minus fourth. So here's what you're tempted to do, is go, oh, that's also the concentration of B. But it's not. So if B starts at 0, which it does, then you have to figure out what you lose from A to get 7.5 times 10 to the negative fourth, because that's how much B that you're going to form. Okay? So when you do that out of that calculation of the 0 order, and you figure out what the concentration of A is at that point, that's at your equilibrium line. To get the concentration of what B is at that point, you have to figure out what you lose from A that gets added over here to B. So that answer on C, on question 34, would make an GPA times 10 to the negative fourth.
Okay.
On 37, that K value should start with a 9. Your half-life, hopefully I'm retired by that number. It's going to be in the mid-70s. If I'm still teaching in my mid-70s, that's scary. On 39, because it all kind of fits together, on 39B, that answer should be around 700 seconds. On 41, that answer should be between 0 and 0.2. On 42B, that answer is an ish around your age. What?
Did you say? How good of a GPA?
We need a better
is C?
gap for C.
On what?
34 C.
34C?
Like 2.5 or like 3.
2.5.
Okay.
It's subtraction.
Like that?
No.
Yes.
Yes.
I don't like that. That's my.
Can we
I
get
love that.
values on
What? God!
39C?
On which one?
39C?
They go from around 300
So bad right now.
to around 3,000.
Wow.
So I think,
It's quite a gap.
Well, but there's 3 different answers that you
I
need.
don't know.
Forty-one.
How around 300?
Or can we just have the day to work on this?
Hey, what order do you want it stapled in?
What do you need?
Weird. Code.
I'll bring
It took 143 seconds for 50%, right?
Okay, but what about the, was it?
7.5%, right?
On which one?
41 and
And that X is gonna be what?
Oh, I think you're talking about on this.
Oh, sorry, no, on the technical one.
I don't know what you're asking.
Oh, I see. Okay, so.
What equation do I use?
Okay? You have the half-life.
You have
It's first, it just did, it just gave you the temperature.
That doesn't matter.
No,
They're just trying to throw you off.
they're just giving you that as background
So they're
information.
walking through and the temperature
Yeah.
doesn't matter.
Yes, basically.
Thank
Yeah.
you.
You're welcome.
I don't like that.
I'm
They're
sorry.
quite mean bugs.
I don't care.
You're 7.5.
I will write to them and tell them.
Ollie Lane said that you're a
You
meanie
take,
butt.
Paul Lane said that you're a meanie butt.
Holly Christmas Lane said
Yes.
No, that still doesn't make
that you're a
Holly
meanie butt.
Christmas, Nicole Lane said that you are a meanie butt and she's not like
it's still, it's
They'll
still.
go, well, what do we have to do to fix that?
Quit your job.
Oh, it's like 100 million professors.
Get rid of him.
Well, we kind of need it.
So, what are we saying?
Kind of do.
I don't think it's that.
We're
39.
getting rid of
What do you have on
funding for
39?
research anyways, so might as well just
Yeah.
get rid of the whole disciplines of science.
Do we have the same?
You know, my
percent
job
as
is just gonna be gone. I'm getting the card for nothing.
It's okay, my job
Because
is.
I just divided it by 2.
It's okay.
I want it to be an academic. We're going.
Yeah, but
No, wouldn't you divide
That's okay. Don't care.
don't
If we-
Don't
One.
care.
it's gonna be fine.
Are there
I'll
any jobs
just,
in the government? I can't. Don't think so.
am I gonna be with it before dinner? Probably
Would you
not.
divide by?
Don't care.
This is.
100
I don't
minus
see
45 is 55, not 65.
I'm just gonna solve it.
Wow.
I don't. think-
Okay, that kind of summarizes the day though.
My bad, King.
I just,
Thanks, Brooklyn.
this is first.
Whoa.
That kind of summarizes the day.
It's not.
Perfect. Questions for you?
Huh?
Questions, if that was a matrix, I was literally going to stone for and break down front by.
I just saw some things that I read that I was like, oh, interesting.
What is the degree constant?
Oh, cool.
I can't go to bio.
I'm flipping
Thanks,
out.
Bert.
What is this?
Okay. Oh, okay. You lied. You lied.
What? He's just like,
My hair is pissing me off.
oh,
I'm gonna go bald.
What? What?
We should all do
I'm
it.
gonna go bald.
I'm telling you, front row, we all
My
should.
hair's making me upset. Before the AP Chem exam,
Huh?
Right
we're
before
gonna
the
go bald before the AP
exam.
Chem exam. So like my hair won't get
My
my
grad
way.
cap will sit so much better.
True. Dude, the grad caps are so ugly.
You 280.
I'm gonna get one of the head caps. I'm getting it done. I'm gonna Amazon it today.
Low-key, that's gonna be official. I need to figure out a cute way to wear it before pictures.
Yeah, they're on Tuesday.
I can't do this. That means I also have to like wake up early on
Okay.
Tuesday and like look nice.
So this is
It
also.
also means, how am I supposed to
Just
carry my,
dude, I don't know.
yeah, I know.
Dude, can you write a
I'm
ratio
not
for 23?
Are we doing good?
Am I just gonna wear it in?
Or is that not good?
Just wear it into school.
I just want my breath to.
I was doing good, and then somewhere last week, school just came out of nowhere and landed the right hook, and I was like,
I only use it when I make this.
Could I write a ratio on 23?
We have K, right?
or
A and C.
What does it ask for? Does it ask for a
It
ratio?
says indicate how the rate of disappearance for each reactant is related to the rate of appearance.
Oh, yeah,
So I can just write a ratio?
yeah.
Cool.
I literally.
Okay, so here's the last kind of theoretical thing about all of this. Let's get us ready for that big lab next week.
No way.
Kevin, what did you?
Kevin, are we still recording? Kevin, are we still going?
Yeah, we are.
That makes me excited.
All right. So actually stop that, Kevin, for just a second, and then we can restart it.